Greetings everyone. My name is Muhammad Ashraf bin Ebihan and I would like to present my final year project entitled Flight Dynamics and Control of a VTEL Chama UAV. Before that, I would like to express my gratitude to all the persons that involved in finishing my final year project, especially my supervisor, lecturers, panels, and also my fellow friends. Unmanned Aerial Vehicles (UAV) can be described as one of the class of aircraft which does not need any pilot on board, consisting of the aircraft equipment, sensor payloads, and also the ground control station. The UAV, also known as a drone, can be controlled by using control equipment from the ground. A big achievement for UTM researchers as they successfully came out with their own Unmanned Aerial Vehicles UAV, which called as CHAMA. The CHAMA-1 is the earliest design with comprehensive data from simulation and wind tunnel testing, while the latest CHAMA-3 was developed through the Computational Fluid Dynamics CFD. Hence, in relation to my case of study, the flying qualities need to be quantified for CHAMA-3 UAV. To ensure that CHAMA-3 respond efficiently, a controller needs to be designed by taking the aspect of longitudinal and lateral dynamic stability. Thus, the significance of acquiring the aerodynamic stability coefficients and derivatives in order to analyze the performance and stability of CHAMA-3 need to be conducted. Alright, first of all, let's move to the problem statement. So in relation to this case of study, the flying qualities need to be quantified for CHAMA UAV in terms of stability and also the control characteristics. This is because it can take a long time to react with the input response. Hence, an evaluation of flying qualities need to be taken to ensure it having a good stability. And finally, I need to design a controller in scope of longitudinal and lateral motion. So for the research objective, it's actually related to the research questions, which is the first one is to evaluate the flying qualities of the open loop CHAMA. The second one is to analyze the longitudinal and also the lateral stability by determining the derivative of CHAMA, and also finally to design the pitch, yaw, and also roll controller for CHAMA-3 UAV. So for scope of study is the first one, I need to estimate the longitudinal and lateral stability coefficients and derivative by using the semi-empirical method. The second one is to determine the transfer function in terms of longitudinal and also lateral motion by using the MATLAB software. And the third one is to analyze the pitching, yawing, and also rolling for the open loop stability of CHAMA. And the last one is I need to design the pitch, yaw, and roll controller for the VTEL CHAMA UAV. So let's move to some of the literature review conducted in this study. It's about the aircraft flight control system, which is for the flight control system, it is actually divided into two types of control, which is the first one is primary controls and the second one is secondary controls. Alright, next move to the research methodology. The first one is I need to know the aircraft specification for CHAMA UAV. Hence, the specification of VTEL CHAMA UAV has been obtained by Tanzia in 2019, which is, so this is all the specifications of CHAMA UAV. And in this case of study, my flight case is at velocity trim about 12.8 meter per second and also at sea level altitude. So this is the parameter and the sizing of CHAMA-3 UAV. Next, this is the dimensionless and dimensional derivatives in terms of longitudinal and also the lateral stability, which is, this is provided by the USAF.com, which is I need to use all this formula to obtain the derivatives. And then this is the results, the derivative obtained by Tanzia in 2019, which is he is using wind tunnel method to obtain the derivatives. So I'm taking this as reference because of if you obtain the derivatives by using the wind tunnel testing, it is much more better and it is much more precise. Next, for state space modeling, after I obtain all the derivatives, I need to transform them into a state space matrix in terms of longitudinal and also the lateral dynamics. So from the state space modeling, I can obtain the characteristic equation and I can obtain the transfer function of the system. And finally, the flight control design, which is include the stability augmentation system and also the control augmentation system. So in this study, I divided the flight control design into two types, which is the first one is classical control theory and the second one is modern control theory. So in the classical control theory, there are stability augmentation system, which is it is using a pitch rate feedback for the pitch angle system. It can improve the damping ratio and also the natural frequency. And meanwhile, for the control augmentation system, it is also consists of a feedback for the output where the error difference is fed to a PID controller so that it can improve the tracking performance. So I'm using a PID controller in the control augmentation system at the outer loop. So the PID controller is actually to read a sensor, measure the required output of the actuator and measuring the proportional, integral and derivative response and combine all the three parameters to determine the output. So for the PID parameters, there are two types in obtaining the PID parameters, which is the first one is Ziegler-Nichols method and also the second one is by using manual tuning method. And for the modern control theory, I'm using a full state feedback or pole placement method, which used to place the closed loop poles of the system in predetermined position for the design of state feedback controllers. Poles are located corresponds as the eigenvalue of the system, hence it can give a lot of effect to the system's characteristics. And then we move to the preliminary results, where I obtain the dimensionless and dimensional derivatives in terms of longitudinal and also the lateral stability. And then I transfer it into a state space matrix form and obtain all the transfer functions. And this is the open loop evaluation, which as you can see for the pitch rate response, it behaves quite badly. For the flying qualities for a short period, it is actually already level 1, but we need to obtain a good level 1 flying qualities and we need to enhance the time response of pitch rate system. Same goes to the lateral stability, which is this is the state space matrix form and it is divided into two because of this one is due to rudder deflection and this one is due to aileron deflection. And this is the two types of time response. This is also the same where the roll and dash roll is already in level 1 flying qualities, but for this study we need to design a controller so that it can achieve a good level 1 flying qualities and we can improve the time response of the system. For results and discussion, the first one is I'm using the classical control theory. So for pitch angle control system, this is the block diagram and this is the requirement. I'm taking the short period thumbprint chart as reference and also the open loop root locus to obtain the PID parameters by using the Ziegler-Nichols method. So this is the time response by using the Ziegler-Nichols method with the input of 10 degree pitch angle. As you can see, it behaves quite badly. Hence, I'm taking an initiative to use the manual tuning method, and then this is the new PID parameters that I obtained, which the time response are better compared to the previous one, and the rise time, settling time, and also the overshoots are within the specific requirements. This also works the same for the yaw attitude control system, which is this is the block diagram. This is the specific requirements and also this is the open loop root locus. So by getting the PID parameters by using the Ziegler-Nichols method, the response have been plotted and it also behaves quite badly. So after that, I'm using the manual tuning method to get the new PID parameters and the response behaves better compared to the previous one, where the previous one its settling time can reach up to 300 seconds. Meanwhile, for the manual tuning method, the settling time only took around 0.815 seconds, and the overshoots is below than 5%. And finally, for roll angle control system, this is the block diagram, and I'm not using the PID controller in the control augmentation system, but I'm using a simple gain. This is because for the roll angle, it is quite simpler and it is less sensitive compared to the previous two control system. So this is the requirements, and also the feedback and amplifier gain KQ and KA was tuned to be 0.3 and also 2.52, and then the response was plotted as in this figure, which is, as you can see, its response are quite good, which is the settling time only took 0.97 seconds, and it is also satisfied the design specifications, which is the damping ratio is around 0.949, and the natural frequency is about 14.8 radian per second with 0% of overshoot. Meanwhile, for the modern control theory, for pitch angle control system, I'm taking the CAP chart as an reference to obtain the specific requirement, and at the same time I need to obtain the level 1 CAP. So this is the equation, and this is all the steps on how to get the gain, the feedback gain, K1 and also K2, and then both response from the from the classical control theory and modern control theory are plotted in the same graph. And as you can see, the modern control theory are having a better characteristics compared to the classical one. And for your attitude control system, the lateral directional dynamics response level that have been conducted by Kuhn in 2011 are taken to be as reference to set the requirements of your attitude control system in this modern control theory. So it is also the same. This is how to obtain the state feedback gains K1 and K2, and then after obtain all the gains, the state response for modern control theory have been plotted, includes the classical control theory as well. So as you can see, this is also brings the same result, where the modern control theory have a better characteristics compared to the classical control system. And finally is for the roll angle control system. The lateral directional dynamics response level by Kuhn in 2011 also been taken as reference for this roll angle control system, but this one's the results is quite different compared to the other two controller, which is for roll angle control system, the classical control theory method brings a better result compared to the modern control system. This is because its rise time is shorter, the settling time is also shorter compared to the modern control system, and the overshoot is 0% of overshoot. So we can conclude that the classical control system is better for the roll angle control system compared to the modern control theory. And then finally, we move to the conclusion, whereas the project was successfully conducted as the value of coefficients and derivatives can be obtained by conducting the semi-empirical method with the guidance of USEF.com. By using the state space approach, multiple equations can also be resolved simultaneously, followed by the obtaining of the transfer function. The evaluation of line qualities also is important to determine the stability of the aircraft before designing the control system. The objective also has been successfully achieved by creating the flight control system, which are pitch, yaw, and also the roll angle control system. And finally, the stability of each control system has been increased and enhanced to reach up to good level 1 flying qualities with various approach of control design. So that is the end of the presentation. Thank you.